Okay, now we are move on to section 1.3 and 1.4. Up to section 1.2, we have dealt with ideal gas, right? Three limiting laws and ideal gas law, etc. And we are living in real gas environment, right? All around us, air basically, nitrogen, oxygen, and etc. Mixture of them are real gases, not ideal gas, right? And obviously, real gases are quite different from ideal gases. So what is different? In this section, we'll deal with those differences between real gases and ideal gases. The most important property which differentiate real gases from ideal gas is molecular interactions. When we define ideal gas was assumed to exhibit no intermolecular interactions, right? But real gases have molecular interactions. As you all know, attractive interactions or repulsive interactions. So that makes difference between real gas and ideal gas behavior, some of which are given in several different ways. So we'll deal with those differences. Okay? And we also introduce van der Waals equation, which is an equation which can describe the behavior of real gas in analytical form. Okay? We'll introduce what this is, how it looks, and how it represents real gases in some manner. And we'll introduce principle of corresponding states. So let's introduce one by one. So real gases have molecular interactions. Two different kinds of interactions: repulsive interactions and attractive interactions. You might be familiar with this kind of diagram, right? From general chemistry class, right? If there are two gas molecules, x-axis is separation, the distance between two different molecules, and y-axis is potential energy. If these two molecules are really close to each other, there is repulsive interactions because of those nucleus of each atoms, right? Or molecules, right? So, when the molecular distance is really short, there is repulsion. Repulsion is dominant compared to attraction. On the other hand, when the separation is relatively large, attractive interactions between molecules are dominant because of van der Waals interactions, dipole-dipole interactions, etc. Right? So, as I just told you, if the molecules are close to each other, close to one another, repulsive interactions are dominant. And since it is repulsive interactions, it assists expansion of gas. At this range, when they are close to each other, they don't want to be close to each other, right? They want to expand those gas molecules, right? And this condition, when molecules are close to each other, is operated at high pressure. When pressure is really high, gas molecules tend to be close to each other, right? They are forced to be close to each other, right? So at these conditions, repulsive interactions are dominant. How about attractive interactions? As I mentioned, when the interparticle distance is in moderate range, attractive interactions are dominant. Okay. So it is operated at moderate pressure, relatively moderate pressure. And since it is attractive interaction, it assists compression of gases. They want to be closer, so they help to be compressed from each other. Okay? So if I summarize, in terms of pressure, at high pressure, repulsive interactions are dominant. At moderate pressure, attractive interactions are dominant. How about at really low pressure? we already learned from previous section, right? At really low pressure, when pressure approaches zero, real gases behave like ideal gas. Okay? So in terms of pressure, we can differentiate the situation for real gas. So real gases and ideal gases are different. So we want to represent it in terms of some quantitative way. One way to represent it is in terms of compression factor. So what is compression factor? So the definition of compression factor is like this. Basically, compression factor is the ratio of molecular volume, gas molecules volume, divided by gas molecules, the volume of ideal gas. The ratio between, let's use the, sorry. So the compression factor, the definition of compression factor is like this. Compression factor Z is defined as Vm over Vm naught. So this one is volume of real gas, and this one is volume of ideal gas. Just simple ratio between these two gases. Okay? Okay. Z is the ratio between ideal gas and real gas. Since the volume of ideal gas V is P nRT over P, we can have this expression for compression factor, Z equal PVM over RT. Okay. Here Vm is molar volume, volume divided by number of moles. So since the definition of compression factor is like this, for ideal gas, Z equal 1, right? The volume of ideal gas and the volume of real gas should be same, right? So it's 0. At intermediate or moderate pressure, when the attractive interactions are dominant, right? It assists compression, right? So the volume of real gas would be smaller than the volume of ideal gas. That's why Z is smaller than 1. Okay? At high pressure, repulsive interactions are dominant, right? So it assists expansion of gases. So the volume of real gases are larger than the volume of ideal gas. That's why compression factor at high pressure is larger than 1. Okay? As you see from this figure, it shows the compression factor Z as a function of pressure for various gases. As you see, when the pressure is relatively small, like at moderate pressure, here compression factor is smaller than 1, right? At high pressure, when repulsive interactions are dominant, compression factor is larger than 1. Okay? There are other ways to represent the differences between real gas and ideal gases. Since real gas behavior is different from ideal gas behavior, and since the volume of real gas is different from the volume of ideal gas, it can mathematically easily be represented using real equation. You learned it from like calculus class, right? Basically, using infinite power series. You use, for example, if you express PVM, the first term should be the ideal gas equation, right? RT. And we add more and more infinite series of values, right, to represent the difference between real gas and ideal gases like this. We use infinite number of variables, right? So these equations are called linear equations of state. So we put different constants, b prime, c prime, b, c, something like that, right? So let's say if p equal 0, then it is close to ideal gas law but not exact, because this side also is equal to 0, right? So when p approaches 0, p is near 0, the real gas behaves like ideal gas, right? Okay. As p increases, as the pressure increases, then it would behave like real gas, right? There will be attractive and repulsive interactions, right? P increases, right? Then we cannot really ignore these terms, right? Which means that the real gas behaves like real gas, right? Different from ideal gas. Okay? As P gets higher and higher, the additional terms contribute, right? We cannot ignore them anymore. Okay? So we can use many infinite series of variables to describe the behavior of real gas. Okay? Since we use infinite number of variables, it can exactly describe the behavior of real gas. Okay? That's the pros of real equation. But the problem is we need to use infinite number of variables, right? So it's not really useful in terms of dealing with, like in terms of describing the behavior of gases mathematically or analytically. Okay. We mentioned that the ideal gas law is limiting law, right? Real gas behaves like ideal gas when pressure approaches 0, right? But that statement does not mean that as P approaches 0, all the properties of real gases is same as those of real gases. Okay? For example, this boil temperature is an example for that. Even though P approaches 0, not all properties of real gases correspond to those of perfect gas. Okay. For perfect gas, compression factor Z is equal to 1, right? So if you differentiate Z as a function of P, dZ dP should be equal to 0, right? Because Z equal 1, right? But in real gas, if you use the linear equation of state for real gas, if you, here is the expression for linear equation, right? So here Z is defined as PVM over RT. If you divide both sides by RT, this part you can get the expression for compression factor Z, right? And you take the derivative as a function of P, and you get this expression, right? If the pressure approaches 0, does this approaches 0? No, right? It approaches to this constant B prime, right? B prime could be 0, but not always, right? It could be positive number, it could be negative number, depending on the situation, right? For real gas, if you really calculate or measure experimentally this variable, dZ dP, as a function of pressure, which is shown here in this diagram, y-axis is Z, x-axis is P. Depending on the temperature, compression factor behaves a bit different, right? At low temperatures, it looks like this, as we saw in previous slide. Right? At high temperature, it is like this. And dZdP here is the slope of this curve, right? At lower temperature, the slope is negative, right? So this number, d prime, is negative, right? Here. Slope as pressure approaches 0 near here. At high temperature, the slope near here is positive, right? The constant d prime is positive. Which means that at a certain temperature, the slope of this curve as pressure approaches 0 near here should be 0. There should be some point, right? There should be a specific temperature at which the slope of this curve, or dZdP, corresponds to 0, right? That temperature, that specific temperature, is called boil temperature. Okay. At other temperatures, dZdP is not 0. Okay. dZdP is 0 for perfect gas, but for real gas is not. But at this specific temperature, boil temperature, it corresponds to 0, which means that at this temperature, real gas corresponds to an ideal gas. It's totally same. At this specific temperature, as pressure approaches 0. Okay. It shows a real example for boil temperature. As you see, this is the visual equation for methane up to 400 bar at 350 degrees C. As you see, as temperature changes, the constant B prime changes, right? As you see, at low temperature is negative, at high temperature is positive. There should be some specific temperature between these, right? Between 200 and 250 degrees C, at which this constant is 0, right? It is shown here, right? It's 0 around here. Okay. Another important properties of real gas, which is different from ideal gas, is condensation. Let's look at this diagram. Pressure as a function of volume. For ideal gas, pressure as a function of volume is isotherm, and it has a form of hyperbola, right? Remember? Hyperbola. As we change the volume, it just changes the pressure. Nothing happens else. Nothing else happens. But in real gas, if you decrease the volume of gases, it does not only increase the pressure of the gases, but at some point, at a certain temperature, condensation occurs. You know what condensation is, right? Condensation is physical change from gas to liquid, right? So let's see an example of a specific gas, CO2. What happens when condensation occurs? Okay, let's see. Let's assume that we put this CO2 gas inside of a piston, right? And we decrease the volume slowly from high volume to low volume. We just simply decrease the volume. What would happen? At relatively high temperature, like here, it basically follows Boyle's law, right? It looks like hyperbola, right? That's no problem, right? We can understand it. But as we decrease the temperature of this gas, it is quite different from Boyle's law, right? What would happen? Let's follow this line from A, B, C, D, E. Okay. We start from here. We decrease the volume of gases. we approach B and C. Up to C is not bad, right? As we decrease the volume, pressure of gases increases. But after the point C, a liquid appears. Liquid. Not only gas, a liquid also appears inside of the piston, right? And it does not increase the pressure anymore. It follows this line. Pressure is constant, but the volume is decreased, which means that there is the more and more amount of liquid forms from C to E. And at the point E, every gas molecule is condensed to the liquid. Here, all the molecules are liquid. Example is almost entirely liquid. Okay. Since it is liquid, it is extremely difficult to decrease the volume anymore, right? Even small decrease in volume increase the pressure significantly, right? So real gas behaves like this at relatively low temperature. A, B, C, and condenses and liquid. Okay? There's a very difference between real gas and ideal gas. As you see in this diagram, there is specific temperature at which it behaves like this, right? Here, this point. Okay? At a relatively high temperature, the real gas behaves like basically follows Boyle's law, behaves like ideal gas. At low temperature, it condenses, right? At a certain temperature, for CO2 at 31.04 degrees C, it follows this line, like this and this. There's a certain specific point, right? It does not really condense, but just pass through this specific point and increase. That specific point is called critical point. Okay? At this temperature, at this point, at this critical point, liquid does not form. Condensation does not occur. Okay? It forms very weird phase of matter, which is called supercritical fluid. We'll cover this part later in chapter 4 maybe. Okay? Anyhow, at this specific point, at this critical point, gas molecules behave very weirdly. It's not like liquid and gas. It is something in between, liquid-like and gas-like. Okay? So the physical variables at this point are called critical constant. Okay? Critical pressure, which is denoted as PC, critical volume, VC, critical temperature, TC. So the critical temperature for CO2 is 31.04 degrees C. Okay? So we saw what are the differences between real and ideal gases. And to describe it, we introduced real equation of state, basically using infinite power series. But as I mentioned, it's not really useful to infinite number of variables to describe mathematically the behavior of gases, right? So many scientists try to describe the real gas behavior using relatively simple equation. Okay. The most important one is van der Waals equation. So basically the equation looks like this. Okay. Up to here, it is ideal gas equation, right? It is a bit different from ideal gas equation, right? Here's ideal gas. On the denominator, there is minus NB, and there is minus A times N over V squared, right? There are two coefficients, A and V, which are called van der Waals coefficient. Okay. So it looks quite simple, right, compared to virial equation of state, but it fairly well describes the behavior of real gas, the difference between real and ideal gas. How? How does this simple equation describe the real gas behavior? So as I mentioned, there are two different constants here, A and B. Okay. And the first term, A, represents the attractive forces of molecules. Okay. And NB minus NB here represents the volume in which molecules can move. Okay. V minus NB. Okay. If you recall, the difference between real gas and ideal gases are molecular interactions, right? There are attractive interactions and repulsive interactions. So to describe real gas behavior, we need to include those two interactions, right, in the equation. So this part basically represents the attractive interaction, and this part basically represents the molecular size, actually. Because for ideal gas, we totally ignore the molecular interactions. So there is no need to consider molecular size, the volume, right? Molecular volume itself. But in real gas, molecules have volume, so it cannot occupy the whole container, right? It cannot occupy where the other molecules occupy already, right? So basically, this simple equation basically adjusts those two parts to describe the real gas behaviors. So how does that do that? The first part, in van der Waals equation, V is replaced by V minus NB. Okay? So here N is number of moles, right? So in ideal gas law, we basically use V, but in real gas, to describe real gas, in van der Waals equation, we use V minus NB. Why? As I told you, molecules themselves have volume. We have a certain container, and if there are other molecules, then a certain molecule, one molecule, cannot occupy those volumes that other molecules occupy, right? We need to delete that amount of volume, right? So this expression basically adjusts those amount of volume that all the molecules occupy, right? How about this? We basically use, this is the expression for pressure, right? We delete it, like basically this amount, A times N over V squared, is subtracted from pressure. Why? Why we need to subtract this amount? Because real gases have attractive interactions. Okay. Pressure. Remember, pressure is originated from forces, right? Forces that gas molecules exert to the wall of the container, right? But in real gas, molecules have attractive interactions. Attractive interactions basically reduce frequency and forces of collisions, right? molecule try to hit the wall like this, but there are other molecules around this molecule. They are attracted to each other. Because of that attraction, frequency and forces of those hitting are reduced, right? So we need to subtract some amount of pressure, okay? And the frequency and forces of collision, both of them, are proportional to concentration, expressed as number of moles divided by volume. Both of them are proportional, so we need to multiply twice n over v, so n over v squared, and we put some constant a, okay, and we subtract, we put minus sign to describe the behavior of real gas of the pressure, right? So this simple equation, by adjusting the molecular volume itself and by adjusting the pressure of gas molecules in real gas reduced by attractive interactions, are shown like here. And it matches fairly well with the real gas experimental data. Let's see that. So if you plot the van der Waals equation using computer, right, using some kind of mathematical tool, it looks like this. At high temperature, it behaves like Boyle's law, right? Same. At relatively low temperature, it behaves like this. Right? As the volume increases, pressure increases, and there's some kind of loop, and it increases again. In real gas, actually, remember, real gas, condensation occurs. But this simple van der Waals equation cannot really show this condensation. But it is relatively okay, right? Compared to Boyle's law, right? So it here shows this kind of loop. So to describe the real gas behavior more exactly, you can do a process called Maxwell construction, which is very simple, which is basically replacing loop by horizontal line. If you have this kind of loop, you just put the horizontal line here, and it looks like condensation, right? So by doing that, we can easily describe the behavior of real gas. So here shows the comparison between van der Waals equation and video equation. I already explained about video equation, right? It pretty much gives us accurate measurement, right? Because we use infinite number of variables to describe the behavior of real gases. Okay? But since we have many variables, it is not really easy to do mathematical calculation by our hands, right? We can do it during using numerical analysis, right? Using computer. Okay? But van der Waals equation is very simple, right? We can do analytical expression, mathematical calculation by our hands easily, right? But there are some limitations, right? Because it is too simple. Okay? There are also other types of analytical expression to describe real gas behaviors, but van der Waals equation is the most famous one. Okay, you will see these equations too in chemical thermodynamics class in next semester. Okay, if I summarize this section, okay. Perfect gas isotherms are obtained at high temperature and large molecular volumes. Remember, right? At large volume, real gases at high temperature and large volume, real gases behave pretty much like ideal gas. It follows Boyle's law, right? But in real gas at relatively low temperatures, liquids and gases coexist. Condensation occurs, right? Another important part about van der Waals equation is that critical constants, you remember, when we dealt with condensation. Here, three different critical constants: critical pressure, critical volume, and critical temperature. Okay. In this van der Waals equation, critical constants are related to the van der Waals coefficient. There are two coefficients, A and B, right? How do they correlate it? That's very interesting, right? Okay. If you first look at the result about this relation, critical volume, critical pressure, critical temperature of a certain substance can be expressed in terms of van der Waals coefficient. Critical volume is 3B, critical pressure is A over 27B squared, critical temperature is 8A over 27RB. It's interesting, right? Why? Let's derive it. If you recall the critical constant part, okay, at critical point, gas behaves like this. It increases, and after this point it increases, right? Okay. This kind of behavior, mathematically, is called inflection. Okay. It's like this point, right? It increases, and above this point it increases like this, right? This point is called inflection, or in Korean, it's called 변곡점, right? I remember that you have learned 변곡점 in high school, right? And at this inflection, the first and second derivatives are zero, right? Remember from high school? The first derivative and second derivatives are zero. Okay? So from the expression of van der Waals equation here, you take the first derivative, dp dvm. You can easily do the calculation, right? Which is zero, right? This one is zero. And the second derivative also is zero because it is inflation. Okay? If you calculate these two equations, okay, you can easily get these equations. Okay? So I do the derivation in classroom. Okay. Another important thing is, if you calculate the compression factor Z at this critical point, you remember Z, compression factor, which shows the difference between real and ideal gas. So Z is PV over RT, right? So at critical point, ZC should be PCVC over RTC. And if you put these three expressions here, you get 3 over 8, 0.375. That's interesting, right? At critical point, compression factor has a specific number, 3.375. If you look at the table 1.5 in the textbook, okay, you can see the compression factor of the real gases, and those numbers are pretty close to this number. Interesting, right? Although this equation, this van der Waals equation, is a really simple one, it pretty much describes the behavior of real gases well. Okay? Alright, lastly, principle of corresponding states. Critical pressure, critical volume, critical temperature are specific properties of each different material, each different substance, right? different materials have different critical temperature, different critical pressure, different critical volume. If you compare a specific thermodynamic properties simply as a function of pressure, volume, and temperature, it is not really easy to find a common occurrence, common things about different thermodynamic properties. Since critical variables, critical pressure, volume, and temperatures are specific property of each substance, how about we compare thermodynamic properties of various materials in terms of reduced variable, not variables themselves, reduced variable. So reduced variables are defined like this. Reduced pressure is defined as pressure divided by critical pressure of a specific material. Right? Reduced volume is molar volume divided by critical volume of a specific substance. Reduced temperature is temperature divided by critical temperature of a specific substance. Okay? And we try to compare specific thermodynamic variables in terms of reduced pressure, reduced volume, and reduced temperature. And could we find a common occurrence? Something like that. Okay? If you do that, you can find it actually. Let's go back to the compression factor diagram. Remember here shows the experimental data of compression factor as a function of pressure. Okay, as a function of pressure. Okay. Depending on the kinds of materials, depending on the kind of gases, all the graphs are different, right? H2, CH4, C2H4, and H3, all different. If you compare compression factor as a function of pressure. Okay? How about comparing the same compression factor as a function of reduced pressure, not pressure, reduced pressure. Okay? Although we plot different gases, nitrogen, methane, propane, ethane, it corresponds to a single line. Very interesting, right? One line. It's not quite different, as you saw in previous slide, right? It corresponds to a single line. We simply just plotted compression factor as a function of reduced pressure. It's very interesting, right? How does this happen? Let's derive it from van der Waals equation. P is equal to, you remember, nRT over V minus NB minus A N over V square. Okay? From the van der Waals equation, we replace van der Waals equation with reduced constants. Okay? So P is equal to PR times PC. PR times PC. Okay? Vm is equal to VR times Vc here. So we replace all three variables P, T, and Vm with using these three reduced variables like this. Okay. And in previous slide, we got the expression for each of these three reduced variables, right? Three critical constants, right? Vc, Pc, Tc as a function of van der Waals coefficient here, right? We put these three expressions here in this equation, and we got this. Okay. If you rearrange this equation, it's relatively easy. I can show you in the classroom. Okay. We got this expression. PR is equal to 8TR over 3VR minus 1 minus 3 over VR squared. Okay. One thing very interesting about this expression, we started from van der Waals equation. And in van der Waals equation, we had two van der Waals coefficients, A NB, right? But in this equation, there are no A nor B, right? There are no AB. AB are gone. AB, van der Waals coefficient, are specific constant for different materials. Those specific constants are gone. It is basically same for all materials. Same for all materials. So this kind of behavior. Different materials follow the same trend. Different materials follow the same equation. It's called principle of corresponding states when they are compared in terms of reduced variables. Okay? Very simple, right? Although it looks quite interesting, it is only true for a specific series of molecules. Nitrogen, methane, propane, ethane, all of them are quite simple molecules. I'm not sure, you guys are learning the organic chemistry class, right? Nitrogen N2, methane CH4, propane C3H8, ethene C2H4. Relatively simple molecules. For simple molecules, these principle of corresponding states are true. But for much more complicated ones, it's not really true. Okay? All right. Let's summarize the chapter 1. Okay? If you look at the page 911, you'll find the summation of chapter 1. Okay? We learned about gas, right, in chapter 1. If it is perfect, yes and no. If it is perfect, we got ideal gas law, right? Ideal gas law, perfect gas. For constant number of moles and temperature, we got PV is constant. Boyle's law. When number of moles and pressure are constant, we got Charles' law. Similarly, at constant number of moles and volume, we got this. Same. Okay. When we got the concept about molar volume, right? Volume divided by number of moles. Okay. If the gas is not perfect, if it is real gas, there are two basic representations to describe the real gas. The first one is video equation, right? PVM is RT 1 plus blah 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 using power series video equation. And the second one here is van der Waals equation, right? P is equal to RT over Vm minus B minus A. Okay. And from van der Waals equation, we got expression for critical constants. We see PC and TC, and we got the expression for compression factor at critical point. Okay. Okay. So this is the end of chapter 1.